7th grade, we are on lesson 4.2, constant rate of change. We're going to be talking about proportions, rates of change, proportional relationships. This is a tool that I end up using in a lot of my math and real world situations, so an important one to make sure you gain. So first vocabulary I want to cover is a proportion. A proportion is a statement that two rates or ratios are equivalent. So here's an example that 1/2 is the same thing as 2/4. And if our brains need to see that, if I have pizza and I cut it into half and I get to eat one of those, is it the same thing as if I have a pizza, same size, cut it into 4 equal pieces and get 2 of them? Yes, that's the same amount. So that's what this is trying to say is it's just cut differently. They are an equal ratio. And what's cool about that is if it is in fact an equal ratio and you weren't sure, you wanted to check it, you can do that by multiplying the crosses. If they equal each other, then you know, yes, in fact, they are in proportion. So I could do 2 times 2, and I can do 1 times 4. Multiply those crosses apart to see if they do in fact equal each other. This times this, 2 times 2, better equal 1 times 4 if these are in proportion, and 4 does in fact equal 4. And that's super useful to know because a lot of times you're giving these real world situations where you're given 3 of the pieces of information and not the 4th. And if I know 3 of those pieces of information and I know that the crosses multiply to equal each other, I have enough information to be the detective and solve it. And so that's where this lesson, these next lessons will be taking us. Super useful. So the first part of this lesson is just kind of exploring the proportional relationships, like how these look, what they are. So we're going to go ahead and let this take us through what is going on here. So it says, it takes a giant tortoise 3 seconds to travel 10.5 inches. And the diagram shows the rate at which one tortoise moves. Use the diagram to determine the tortoise is moving at a steady pace. Steady pace is a constant rate of change. So they broke down the 3 seconds, 1, 2, 3 seconds. 3 seconds to go 10.5 inches. All together, those 3 seconds are 10.5 inches. They said in the first second, it went 3.5 inches. In the second, it went 3.5 inches. How much did it go in the third? Well, I can put those together, 3.5 and 3.5 plus the unknown amount will all add up to 10.5. And I know that 3.5 and 3.5 together is 7. And refresh of our one-step equations. I want to isolate this variable to find out how much that is by itself. Is together with a positive 7, do the inverse operation, a negative 7. As long as I keep the scale balanced by doing the same to both sides of the equation, that leaves me with x equals 3.5. So he is going at a constant speed. All right, so let's go ahead and answer what they've got here. They use the diagram to determine if the tortoise is moving at a steady rate and explain. It shows that he's going 3.5 inches for each second. Then it asks us, what is the unit rate per 1 unit that's represented in the diagram? And remember, each 1 second is what we're talking about, so that's our 1 unit. So the unit rate would be 3.5 inches per second. We can complete the table. We know in 1 second he goes 3.5 inches. Add those together, which we did already. In 2 seconds, that is 7.0, or just 7 inches. We know after 3 that he goes 10.5. That was the original piece of information. Add another 3.5 to that. That's going to be 13, plus the half more is going to make that all 14. And to go 5 seconds, we have another 3.5 So that's 14, 15, 16, 17 and a half, 17.5. For each column of the table, they want us to write a rate that compares the distance and the time. So distance compared to time. So we're going to put 3.5 over 1. 3.5 distance compared to time is 3.5. On this one, 7.0 compared to time of 2. And if I divide those, 7.0 divided by 2, I end up with 3.5. Next one, 10.5 distance over time of 3. And if I divide 10.5 divided by 3, any guesses as to what that's going to be? 3.5. For this one, distance, 14 over time, 4. 14 over 4. If I divide 14 divided by 4, I will end up with 3.5. And 17.5 distance over 5 time. 17.5 divided by 5 is, you guessed it, 3.5. So what we learn is that the constant rate of change is 3.5, the unit rate, 3.5 per second, inches per second. So what do we notice about the decimal forms of these rates? They're equal. And how do you think the distance the tortoise travels is related to the time? It continues at a constant rate. So that's what they're after there. So with rate of change, the definition of that is a rate that describes how one quantity changes compared to another. Example, distance over time. How does time change? How does distance change in comparison to how much time is passing? Another example, miles per hour would be distance over time. Unit rate would be if that is to a 1 hour. But the rate of change can be done in more than just a single unit. We could say 60 miles in 2 hours or something like that. We would break that down to a unit rate of a 1 hour, just so that we can compare it or have an idea for how that's working. And proportional relationships definition is a constant rate of change, so the ratio stays constant or the same as it goes along. Keywords you'll hear in that are per or for each. I call these my handlebars. I mean, I call them proportional relationships, but you'll also hear me say, I can't ride my bike without my handlebars. I can't do my math without my handlebars. So I call them that because I have a ratio equaling another ratio, and I don't know why I thought that looks like bicycle handlebars, but to my crazy brain, that looks like bicycle handlebars. So I use those bicycle handlebars. This is the tool I use for proportional relationships. And I'm going to take you back earlier when I mentioned if I have 1/2 and I say that is equal to 2/4, that these are in proportion to each other, I can check that and make sure that's true by multiplying my crosses. 2 times 2 has to equal 4 times 1 if they're telling me that these are equal or these are in proportion to one another. And 2 times 2 is 4, 4 times 1 is 4, so yes, they are in proportion to one another. That's true. That's super useful if I know 3 pieces of information on my handlebars, on my proportional relationship. Let's say I have these 2 ratios, this ratio and this ratio, and let's say I know that this is 5/10, and I know that this is 20, but I don't know that value. I mean, there's a couple ways to do it, but one way that's super easy for me is to say, all right, I'm going to use this skill, multiply these, and they have to equal each other because it says these ratios are in proportion to one another. So I will multiply 5 times x, which will just give me 5x, and that has to equal 10 times 20, still 5x equals 10 times 20 is 200. And then from here, I'm just isolating variable, one-step equations. Here is my variable. It's being multiplied by 5. I do the inverse or opposite operation to undo that multiplication. So instead of multiply by 5, I will divide by 5 to isolate the variable. I have to do the same thing to the other side of the equation to keep it in balance. 5 divided by 5 is 1. That leaves me with the 1x there. And 200 divided by 5 is 40. So this x, in order to be proportional, is going to have to be 40. So I use that tool a lot anytime I'm giving some sort of a rate, miles per hour, or anything like that, a ratio relationship between two items. So what was the vocabulary word they gave us for that? The rate of change. The rate of change is what we were, the two items that we're comparing to each other as a ratio. And I may have gotten ahead of myself on the last part where they get into that later, so you just might have gotten a sneak preview, I don't know. But let's go back and get that rate of change and the constant of proportionality explained. So the next part of this lesson talked about constant of proportionality. And the constant of proportionality is frequently referred to as variable of k. I don't know why k, there's no k in there, but whatever, constant for the same sound, k, constant. Anyways, it's frequently referred to with the variable k, and it refers to the relationship between x and y, like x being a set of data and then getting y as the result of that data. To find the constant of proportionality, you could say k will equal y divided by x, or y over x, y divided by x. So you flip the way the table has it, over y divided by x. So we're doing cost over pounds to get a unit rate. So cost over number of pounds. You see here they do the 19 over 2 because k, the constant of proportionality, equals y over x. And I get $9.50. Is that money? Yep, $9.50 per pound. And then we do, hopefully, if this is constant, then we better get the same out of this ratio too. $28.50 divided by 3 pounds, and yay, we get $9.50. And if this is constant, then 76 divided by 8, 76 divided by 8, the unit rate will be $9.50 per pound. And so this is all equal to $9.50. They are constant, so the relationship is proportional. Constant rate of change is $9.50 per pound for every pound we get. And here's something that gives you a peek into 8th grade math a little bit, something we'll build on next year, is they write that equation as whatever y is, it will equal, in this case, $9.50 times x, where x represents how many pounds you're going to buy. So if you go into the store and you're going to buy a certain amount of pounds, when you know how many pounds you're going to buy, you can multiply it by $9.50 if we know that's what the constant of proportionality is, and that's how much the whole thing will cost you. So that's what this is. This lesson is trying to cover. Hopefully I explained that well enough to understand, but let me know if I need to explain it better.